All right. So let's move to the next speaker. Next speaker is Abhinav Valada. He is an assistant professor and director of the Robotic Learning Lab at the University of Freiburg, Germany. He is also a member of the Department of Computer Science, the BrainLinks Brain Tools Center, and a founding member of the LLIS Unit Freiburg. His research lies at the intersection of robotics, machine learning, and computer vision, with a focus on tackling fundamental robot perception, state estimation, and planning problems, using learning approaches to enable robots to reliably operate in more complex domains and diverse environments. So Abhinav, if you're there.
Yeah, thank you for the introduction. I'm going to try to share my screen. Okay, so are you able to see the screen right now? Okay, perfect. Just a second. Okay, thanks again for the introduction and for inviting me to this workshop. So I'll start with some high-level motivation of why do we need robots in the first place. So let's look at three main reasons that I think I could kind of pinpoint as important. The first, I would say, is demography. And to understand a future of any country, you must first understand how its population is composed of in terms of age, in terms of gender, as well as how this composition would evolve in time. And if we look, most countries in the world today have a low population growth rate, and in even some countries, there's an extreme population decline. And as the aging population has become an inevitable fate, we realize that this leaves us with two big questions: who's going to be taking care of our elders and who's going to be doing their jobs? And our entire society will basically collapse if we have too few workers and too many retirees. And the second, I would say, is automation. So with the latest developments in robotics and AI in the last decade, what we have only imagined a dream probably a decade ago is now a reality. And if we take a path to ensure that learning or AI in general is safe, then we can reach a new model of society, and one that's in general more productive, more efficient, and where machines can reduce work. And the last thing that I would say is survival. So I think we should face it that we are generally doomed at one time or the other. So we have a planet has faced already 5 mass extinctions, and the latest of which is basically wiped out the entire race of dinosaurs out of our planet. And so therefore we can also assume that at one point it's also inevitable that we are going to face another mass extinction, and robots are going to be playing an important role in combating such challenges, from climatic change to establishing life on other planets and so on. So basically this brings us to the motivation in general, which is we need robots to help us to tackle these challenges of both today and tomorrow. So let's first look at a very brief discussion on why learning in general is important. So today we have more robots now than ever in our world. However, if you see that most of these robots are confined to fairly constrained environments, such as in industrial spaces where they perform repetitive tasks, or even most often, more recently in households where they bring us food and so on. And if we take really more extreme complex environments, such as in medical surgery or space exploration, these robots are often only pre-programmed, or they are trained to perform specific instructions. And of course, we all have our favorite cleaning robots in our homes, which are sometimes, I'm sure, like the self-driving vehicles of our pets. And these are not the only ways in which we all envision robots to be used. So what we envision in the future is robots to be performing far more complex tasks. And as you can see here, that these environments are no longer contrived spaces. And we want the next generation of robots to be performing far more complex tasks in these unknown and unstructured environments, as well as in shared spaces in humans and while collaborating with humans. And in order to achieve reliable operation, we must enable robots, of course, to learn interactively and adapt to unexpected situations. Oops. Okay, so let's start with interactive learning. So learning to solve complex tasks from visual observations is a dominant challenge for real-world robot learning. And in order to learn new skills, people often rely on some kind of prior knowledge or an expert teacher that guides the learning process. And here we can see that skills such as walking, writing, or playing some kind of sports, or even driving a car, all of these are learned under a supervision of a teacher initially. So in this work, we wanted to basically see if we can enable robots such as autonomous agents to learn from feedback that's received from a human teacher. So the most common way to use some kind of prior knowledge is using learning from demonstration. And here the goal here is that an expert collects a database of perfect demonstrations, and then the policy is trained to regress the data in the data set, and then the policy is deployed on the robot afterwards. So with learning from demonstration, we have seen tremendous success, and of course it has its own set of limitations. One is that we need to collect lengthy and long demonstrations, which is an expensive process. And it's also not clear as a priori how many demonstrations are needed to train a policy. And this often leads to multiple iterations of data collection, retraining, evaluation, and so on. And most importantly, training on perfect demonstration suffers from compounding errors and also data distribution mismatch. So as soon as the policy basically deviates from this trajectory, it will encounter states that have not seen during training, then this leads often to failure. So here what our goal is to use an interactive setting on the other hand, where the distribution of data is induced by the policy itself, avoiding any kind of data distribution mismatch. So towards this goal, we proposed our approach that we call as ceiling, which is a framework that combines both corrective and evaluative feedback to train a stochastic policy interactively. And the figure here shows two types of feedback that that a human can provide or a teacher can provide. And when the trajectory basically deviates out of a good behavior, then the teacher is not able to correct it. So he or she can just toggle the evaluative feedback to negative, and in order to discard the subsequent state action pairs, he can just toggle the evaluative feedback to negative. If on the other hand, he or she wants to correct the wrong behavior, then we can intervene and bring the robot back to the optimal trajectory. And you can either use joystick or any other interactive interface to do this. And since the collected data typically contains an imbalanced amount of non-corrected and corrected samples, we also use a weighting scheme to increase the prioritization of the former. Okay, so the video here shows how the interventions is provided by means of a gamepad. So this is just one example. You can use any kind of interface. And an important thing to note is that we only need to provide a really small amount of corrections that are necessary. And here you can see with the joystick for the task of opening a microwave. Okay, so how does this work? So policy basically takes an RGB image from a wrist-mounted camera as input, and the image is then fed through 3 convolutional layers, and then the visual embedding output is concatenated with the joint and the gripper positions of the robot. And then we feed this to an LSTM cell that takes account of the sequential nature of this problem. And finally, the output here is a 6-dimensional end effector pose plus a 1-dimensional gripper action. So our data collection again consists of 4 steps. So while the robots interact with the environment, we continuously update the policy, and the update loop runs in parallel in a separate asynchronous thread. And there are 3 steps. First, a batch of labeled and potentially correct trajectories are sampled from the replay buffer, and so on, as you can see here. So goal here is to increase the probability of the policy of picking a right action. And we achieve this using a maximum likelihood objective. Okay, so to evaluate this approach, we performed lots of user studies with a group of 10 participants here. So we both, user groups contain both men and women in the age of 25 to 32, and each participant was given 5 minutes to familiarize themselves with the control interface. And they had to teleoperate the robot during the experiment. So this study was conducted in simulation for the sake of reproducibility, and we evaluated on 4 tasks initially, which is closing a microwave door, pushing a button, lifting a lid, or unplugging different kinds of chargers. So each training run consists of 10 episodes for a duration anywhere between 20 to 30 minutes, depending on the task. And we compared to various baselines that you can see here. So the important aspect, I think, is the table, which shows the different types of feedbacks and the different feedback methods. And we can see basically ceiling proposed method is the only method that can provide corrective feedback, discard wrong actions, and store the right ones. So we evaluated this, as I said, on 4 tasks, and we can see the 4 tasks that are being performed here on simulation. And our trained policy is able to very quickly, within 1 hour of real world training, solve all these tasks. Okay, so the interactive framework also allows the policy to learn complex emergent behaviors. And here we see that the robot is able to understand that the grasping attempt is not successful in the first try, and it then reopens the gripper again right now and attempts a second try. So learning such self-adjusting behavior would not be possible if we just use perfect demonstrations. So we also demonstrated this capability on real robots, and here we use only the human teacher's feedback, no instrumentation of the environment. And we show that Ceiling is able to achieve really high success rates in, again, less than only 1 hour of training. And here you can see that we also show in the video here that a policy is more robust to external disturbances that which were not present during training. Okay, so what we saw until now is basically static manipulation. And of course, we want to scale to many different real world tasks. We also need mobile manipulation. And mobile manipulation remains a critical challenge for autonomous systems in wide range of scenarios, from industry to any kind of home assistant services. But currently, this task is usually separated mostly into a pure navigation task, followed by a static manipulation task. So this is on one hand slow, on the other hand also requires the base poses which can solve the whole manipulation task at one go. And here you can see the one way of doing this is using inverse reachability maps. For many tasks, this is not really possible, as they require the use of both the joints as well, the base, as well as the arm of the robot. And this includes tasks such as the PR2 here opening the door, for example. And more generally, the use of the base and the arm enables large increase in efficiency over sequential and static manipulation tasks. So what makes this really challenging? The first thing that we are confronted with is much larger configuration space that consists of the base and the manipulator. So planning or sampling in such high dimensional spaces is very expensive, and is found solutions can be far from optimal. And approaches that plan in the joint space may require also really expert knowledge to transfer the task constraints from task to the configuration space. And moreover, mobile manipulators acting outside of these controlled environments are frequently confronted by dynamic scenes as well as dynamic obstacles in the environment. And this requires really fast reaction times and adjustment to, the changing circumstances in the environment. And the last thing is that these tasks are typically very long horizon, and they require sparse rewards, which makes them, of course, difficult to learn in an end-to-end manner. So to address these challenges, we recently proposed our approach that decomposes and modularizes the mobile manipulation task. And here we assume the task to be an arbitrary end effector planner, and this is shown in green here, and this generates the motions for the end effector in the task space. And we introduce a reinforcement learning agent to control the base of the mobile manipulator. And here the agent aims to find base motions that ensure that the end effector motions are kinematically feasible. So we frame this as a goal-conditioned reinforcement learning problem. So given its current state and the next step velocities for the end effector, the RL agent here outputs actions for the mobile base consists of linear and angular velocities. And a standard inverse kinematic solver then solves for the arm configurations and produces a dense reward signal and the kinematic feasibility for the motion of the arm. And more specifically, the reward is basically just a simple Boolean indicator, and this alleviates the need for any expensive or task-specific reward engineering. So this decomposition provides very desirable properties. One is that it's very simple and a dense reward signal, and it also helps to for zero-shot generalization to previously unseen tasks. And our planner can also be abstracted from the kinematic feasibility, and it remains very simple. And so there's a wide range of applicability for this. It ranges from different robotic platforms without any expert adaptations to the type of robotic platform that you want to use. So we demonstrate this on 3 different robotic platforms with very different kinematic abilities. So the PR2, the HSR, as well as the Tiago robot. So as you can see here, each of these have different degrees of freedom, different types of mobile bases, different amount of manipulators, and so on. So we implement an analytical environment which integrates the system step by step to generate the robot poses, which allows for fast training. So we optimize our objective with the current model-free reinforcement learning methods. We primarily use soft actor critic, which are shown to be robust to noise. And at training time, we generate end effector motions from a simple linear dynamical system to reach random goals, as you see in this video here, using the HSR robot. So then at test time, we evaluate the zero-shot generalization capabilities of our agent. So we construct unseen tasks from both linear dynamical systems used for training, as well as motions based on human demonstrations from our previous work. And as we can see in this video, all the robots are able to solve these unseen tasks. From the left to the right, we see pick and place, door opening, drawer opening, and from the top to bottom, we see 3 different robots, PR2, HSR, as well as Tiago. Okay, so we compare this with a simple baseline that replicates the end effector motions for the base, and it transforms it as much as into a static manipulation task. We also compare this with geometric modulation, which was designed with expert knowledge about the robot. And you can see our performance of our approach here in bold. And the performance on imitation task does not differ from the linear dynamical system. And this demonstrates that, that we are able to generalize to unseen motions. Okay, so while the baseline was able to solve some of the tasks for the flexible PR2, we can see here that it completely fails for more restrictive differential drive of the Tiago robot or the 5 degree of freedom HSR robot. In contrast here, you can see that our approach achieves high success rates across all of these 2 challenging robots. So these results are in an analytical environment, but we also show that it's very readily executable in the Gazebo simulator. So we constructed a small real world experiment. Initially, this is a bit old right now with the PR2. So we automatically generate random start poses, including very challenging poses. And the agent achieves zero-shot transfer to the real world, which further indicates the robustness and the capabilities of our approach. So quantitatively, the results in the real world closely align to the performance of the simulation, with only a minor drop here in the performance. All right, so this is some more recent work after a published paper. So here we were able to demonstrate that we can transform an arbitrary end effector motion into mobile manipulation task in our first work. But now we want our mobile manipulators to be broadly impactful, and they need to leave the lab. So in particular, they need to be able to act in human-centered and cluttered environments, as you can see here. So these environments introduce further constraints on the feasibility of motions based on collisions as well as obstacles. Here we can see two such environments, such as a bookstore or a very typical apartment. So we extended our approach that I just presented before to incorporate sensor information from the environment. So our main aim here is to generalize to unseen and complex environments, such as we use 2D obstacle maps, and these obstacle maps can be constructed with any sensor, such as LiDARs or any depth sensor. And this gives us fast inference and good generalization to unseen environments. So we also want to avoid obstacles. Furthermore, this can require large movements of the base. And as such, we allow the agent to control the velocity of the end effector motions. So we procedurally generate training environments based on very simple shapes, as you can see here, providing a large and really large diverse training set. And we propose a simple end effector motion generated based on A star with heuristics. And this ensures that the possible path for the base basically exists. And the main heuristic here is A star weights based on inflated obstacle maps from these environments. So navigating these environments further highlights the benefits of our decomposition. Here, the reinforcement learning agent scales very easily to really large maps and collisions with obstacles. And we only need a 2D path planner such as A star to generate longer paths for the end effector itself. And that is in contrast with other planning approaches such as RRT, which spend a lot of time on sampling as well as collision checking. So an important thing here is that our approach is robust to sensor noise as well as obstacle artifacts in the occupancy map of the environment. Okay, so similarly, the RL agent can also instantaneously react and avoid dynamic obstacles in the environment. And in contrast to planning approaches that would require constant replanning, and the only replanning here is the A star planner for the end effector in the Cartesian space. So we require no ground truth knowledge at all here. So everything is purely based on sensor data, where we have here, I think, 270-degree LiDAR, as well as range sensors on the back of the robot. Okay, so this last aspect I want to talk about here is that, so as robots often are transitioning from performing these repetitive tasks in industrial environments to now performing tasks closer to humans and interacting with them. So we also arrive to more challenges or more unexpected challenges that we have not seen before. And here the technical advances that allow robots to perform these complex tasks closer to humans also now represent a risk to safety and comfort. And this, as a result, has led to several ethical discussions about the current learning algorithms, which has increased to show unexpected outcomes because of using these learning algorithms themselves. So one really famous example is in natural language processing, where we have seen these many chatbots present racial and gender biases while learning from large text corpuses. And more recently, we've also seen these examples of autonomous vehicles when they are trained in certain data sets or only evaluated in certain countries. We've also seen both problems in the object detection models to people of color. And similarly, we can also expect these learning algorithms to perform biased outcomes in learning social skills. For example, when robots are navigating in a socially compliant manner, and this can also lead to bias and discrimination in the behaviors. So what we wanted to initially tackle here is socially compliant navigation. So if we think about socially compliant navigation, what are the required skills for robots to navigate in socially compliant manner? So from a technical point of view, the navigation task requires a robot just to go from place A to place B, while here in a socially compliant or a socially aware navigation requires to do this in accordance to social norms or in compliant with social behavior. And from...
Sorry to interrupt, you have 1 minute left.
Yeah, thanks. And from a fairness point of view, this means to provide socially good and avoid prejudice through awareness, as well as with respecting human differences and necessities. So with this in mind, we proposed a framework with 2 different strategies, as we call learning and relearning. And in the first, the learning stage, the robot incorporates social context during navigation, so the robots can navigate in a socially compliant manner. And in the second stage, we call as relearning. Here we use relearning to diminish any bias in the planned paths with the initial navigation model. And the interest of time, I'm going to skip these details. So we can basically do this with inverse reinforcement learning, and this allows to capture the navigation behavior of the surrounding humans in a very accurate manner. All right, so the last thing I want to briefly talk about is the framework for responsible robotics. Very recently, we have proposed the first large survey to do this on how we can develop responsible learning robots. And in this, we show a categorization of different ways that we can achieve responsible robotics using learning. So this can be different ways to tackle bias, data level or model level. This can be in the pre-processing stage in during the learning, as well as in the post-processing stage. So with that, I'd like to thank you for the attention, and I would like to also thank my group here. So the thing that I have presented today is mostly due to their hard work. Thank you, and I would be happy to take any questions that you may have.
Thank you, Abhinav. Very nice work. So yeah, we have one question from the chat. I think Ayush Jain was asking to you and Bram, in your opinion, what is the major challenge or difference between learning for autonomous applications and learning for human-robot collaborative tasks?
I don't know if Bram wants to answer this first. Maybe I can briefly say something. So I think while learning with human, if you're just learning for automation, you don't have these constraints. I mean, you have some kinds of constraints for safety, but when it comes to learning with collaboration tasks, I think there are far more constraints with safety. And I mean, you also have aspects that you want to achieve collaboration, which is not there in general when you just deal with plain automation. And in addition, as I said before, this also has complex ethical and social behaviors. And we're dealing with learning, and I think it's really important, really difficult to incorporate these human norms or these human compliant behaviors while learning, because this really depends on many aspects on where you are using these robots, where these robots are, which countries that these robots were trained on, and where you're deploying them, and so on.
Yeah, thank you. I don't know if there are any other questions from the organizers. Okay, if there are no other questions, I would like to move to the next. Okay, we have coffee break now, so we will come back at 11:20. Hope you will stay with us.